Okay, so the next topic is going to be on diffusion, right? So remember our pathway so far, we were talking about largely text and text relevant topics, and now this is going to go into some amount of multimodality, particularly images. So one or two papers, again a very diverse field, again with every passing conference a significant flood of new topics, new research directions, techniques that become state of the art, improve over state of the art, and so forth. So the first, if you find the little bit of the trace of where these initial successes came out of diffusions, these people from UC Berkeley would be one of the key contributors, right? Denoising diffusion models. Again, I'm going to take a very simplistic view. I'm not going to go into a lot of the mathematics of this. So let us have a big picture in mind, right? Before I delve into x's and y's and theta and phi and so forth, I want us to have a top level view. So what the diffusion framework is that suppose I know a controlled way of converting something like a signal, in this case an image, to something like a nonsense, in this case a noise, right? If I have a controlled way of transforming something like a natural image which has lots of structure, lots of information rich content, how do I transform it into something like with less structure, more noise than information? Then I can also use that controlled manner to learn the reverse operation. The reverse operation being you convert noise back to something of structure, right? We are all constantly in a generative model, particularly in image generative world, you are trying to learn the spatial structure that maps to the world of natural images. So when I have completely unstructured, noisy inputs, how to create that structure is the question that image generation models have to address. So the diffusion then takes the view that compared to say other models previously that existed in the field like a GAN and so forth, which tries to map the distribution of the noise generated output with the true natural images. Here you take a view of knowing a forward trajectory, which also gives you the clue to map the reverse trajectory. Okay, so the forward process, again in terms of terminology, we'll come back to this, is the first one, and the reverse process is the one in the bottom, which is called the reverse diffusion. You try to bring the signal or the image back. Now let's take a more mathematical view of this big picture, right? So what do I have? I have a real data, which is an image in this case, let's say, and now I decide that I have to run t steps of noising, right? And every step is progressively more noisy than the previous step. Okay, so assume that there are t steps, and the simplest way to add this noise is to consider a Gaussian noise, essentially with the same data being used or scaled version of the current image being used. So think of it like if I want to transition from xt minus 1 to xt, I am trying to break this equation. You assume that xt minus 1 is scaled with some scalar value 1 minus beta t, where beta t is a number between 0 and 1, and then you also add to it a variance which is also a beta t in this case, and now you use this scaled image of your previous iteration as the mean, have some variance for the noise, and generate a new noisier version of the image, right? And since it is a Gaussian process, it becomes very simple, right? The approach is very simple in the sense that every step that you do incrementally can also be collectively looked at, can also be looked at in the form of a distribution that starts from the initial data itself, which is the image, and progressively you are adding more noise. So any step can also be represented as a Gaussian expression of the original image itself, just that every step you are adding more noise you are adding a lesser scaling of the original image. So if you start seeing the equivalent of this distribution in a simple mathematical form, let us focus in on this expression and then I will go to that image at the bottom. So you start seeing that every image xt at time instance or your step instance t is some scaling of x naught, and you know that all these alpha t's are progressively multiplying to smaller and smaller numbers, right? So this alpha t bar, which I discussed or put out in the previous slide, more time goes, lesser the value of these. So which means that the x naught in the contribution of x naught keeps going down, right, exponentially. And noise on the other hand keeps increasing. So if you think epsilon is a standard Gaussian noise, the standard Gaussian noise gets scaled up and up and up, and the signal goes down and down and down, which is what you see in the pictorial form. At t equal to 0, you have a clean image. As you keep unrolling in time steps to t, you get almost pure noise. Okay, so any step can also be written as a mathematical expression of the original image scaled with some factor plus a Gaussian noise scaled with some other factor, and the factors that are affecting the signal part are reducing, factors that are adding the noise part are increasing, which is why you see this effect. Now, why do we call it diffusion, right? So when I was reading a couple of years ago, I also had this, right? This is an interesting Markov chain. Why do people call it diffusion, which has completely, at least to my mind then, had a very totally different notion. And then the reason being that if you add small different samples, or in this case small level of impurities in a otherwise, let us say, cleaner liquid setting, the small subset of these particles of high concentration become low concentration, but they diffuse out throughout the rest of the liquid, right? So this is also one of the reason why this modeling framework is called diffusion. Now let's talk about the backward setting, right? The backward setting is really where the learning is, right? This is the reverse Markov chain process. This is essentially, now I want to approximate the joint density of all the data points from x0, which is your clean image, all the way to x capital T, which is your almost pure noise. So this Markov chain of joint density can be seen as a product, right? Remember that every step has only one step dependence. Remember that our forward propagation had the one step dependence. Xt only dependent on xt minus 1. Right? So when I now put the Markov chain, you can now decompose it into this sort of a product, right? Now xt, which comes out of this, now you can think of it that you have reached sufficiently large number of steps, a few hundred steps in sometimes, few thousand steps in some cases, but sufficiently large enough that now xt can be considered standard Gaussian, right? You have a pure noise at that point. And now the rest of the process, which is this xt minus 1 given xt, is purely denoising, right? This is purely the job of your model, a network that has to approximate this p theta, that given a noisier version, it has to give you a less noisy version of the image. So if you want to put the math together and write that as a distribution, again, because the forward process is Gaussian, the reverse process can also be thought of, can also be seen as a Gaussian, can also be proved as a Gaussian. Assume that you have a network to estimate the mean and the covariance of this, right? This is the simplest way to think of it, that if I have xt, I want to generate xt minus 1, I learn the mean, which is a mapping of this xt to a space which corresponds to the mean of the distribution from which I have to sample to get my xt minus 1. And the parameters of such a network is your theta. Similarly, you can also approximate the covariance needed, and you can keep doing this network recursively. You can keep calling this. Every time you get an xt, you go to the xt minus 1, you go to the xt minus 1, you go to xt minus 2, and so forth. So now you can see that from the left to right, in this case we have ordered it in the reverse way. Every step of the way you are removing or trying to remove some level of noise, right? This can be learnt, right? The whole idea being this theta is a parameter which defines a model, and the model can be learned to perform this estimation. In practice, what is done is, instead of trying to predict the mean and the variance of the distribution itself, the practical implementations, you can essentially take the same mathematics and try to predict the noise. Do not try to predict what is the new cleaner image, you predict what is the noise component of it, which you can remove from your xt to get your improved xt minus 1. So, summary, try to predict the noise is better than predicting directly the pixel level cleaner version of the image. So, you put a network that can predict or approximate the noise that happens at time instance t for the input that is given, that is xt, and some expressions for the mean of such a distribution is given here. And then what you can get is, given xt, you have an expression to find xt minus 1, also with a sampling from a Gaussian for the component of the what you can't predict from xt, right? So, just a short summary is listed here. Again, I am not going into how to prove, how to get this mu theta as this expression and so forth. Most of it is in the paper that I cited. But if you ask me to summarize in algorithmic steps, what we do, you start with of course a real image, but when you draw from the reverse side, you start with a noise, and then at every time instance t, you are sampling from this distribution, and then you are returning the xt minus 1 given xt every time, all the way up to the 0th step where you have supposedly obtained a cleanish image. So, how this comes out is basically from a variational approximation. You essentially go through again the math of forming this, what is the optimization function for learning the noise distribution epsilon theta. All I want to say beyond the math is, it turns out to be a simple mean square error reduction, right? While the entire formulation goes through a bunch of mathematical simplifications, a variational approximation and so forth, but the final loss function, when you try to implement it into the PyTorch or your favorite TensorFlow or your favorite ML optimization tool, it turns out to be a mean square error reduction, right? So, that is very simple, property is well known, has been studied extensively well before even large models came into picture. In fact, autoencoders have existed for 30 plus years, right? So, mean square error and its properties through a network are well known, and they are quite stable, and they are robust methods exist to optimize it. So, the simple loss where every step you estimate a model's output and compare it with the true noise that comes in is what is guiding your diffusion model, backward model training. So, let us summarize, right, without or keeping the math that we discussed in the background. Let us summarize what is the diffusion process or a diffusion training process. So, you start off with, let us say, an original image, say some clean image, and then you basically have a forward process. Say you are now looking at one time instance only, a time instance t. So, you have, let us say, an image, but a noisy version of the image through the forward process. Now, this noisy image is what goes into the transformer network, say in this case a diffusion transformer, a UNet is commonly used, a transformer encoder decoder is also used, and so forth. So, if you say some network exists, basically it is trying to predict the noise, right? Given this input to the network which is xt, it is trying to predict the epsilon, right? And that epsilon is coming from the noisy image and the clean image, right? This is the actual noise that you fed in to that noisy image, and this is your ground truth to predict or to hinge the loss function on. This is the target, right? This is the noise that you introduced, and the transformer, encoder, decoder, or a UNet is made to learn, optimize, back propagate to reduce the expected error of the true noise with the model's prediction of the noise that was added. You keep this number of steps, uniformly sample it from a set of distribution. You also sample over a bunch of real images. So that is why you see in the expectation, you see x naught is one component, means you don't train it for one image, you train it on a data set of images. So the x naught itself is changing cats, dogs, cows, elephants, cars, all that. T is basically a uniform sampling. You fix a max range and you say that okay, this is a number of steps you allow. Epsilon is of course a random noise that you are generating through a Gaussian sampler. So you perform the mean square error over the full data set and you train this encoder or decoder model, or in other original formulation the UNet was used. So where is it used? Almost ubiquitously, right? Almost exclusively. In fact, I can say that when I was making these slides, I have used diffusion models for many of the graphics, right? You take your latest Nano Banana or Gemini 3 and so forth, they all use diffusion. So I am basically using diffusion models to explain diffusion and then putting it out as a slide that also talks about diffusion. So all circular. So text to image generation, video 3D, audio speech, medical imaging, data augmentation, robotics, significant use cases of diffusion models, right? The quality of the images that comes out, and typically they are measured in what are called FID scores. Again, I don't have the bandwidth to go into quality estimation of the outputs and so forth, but on certain metrics, let's call it certain metrics, the previous models were completely outperformed by diffusion style models when they came out, right? And therefore it has become the de facto for image generation. So now, then people, once this image generation, right, if you can take a data set of what is called say MNIST, which consists of handwritten digits, if you take a data set of say CFAR images or more natural images in an image net and so forth, you can train this model and you can prompt it and the model's Gaussian noise generates you a very nice looking image which is of that data set. But if you ask me, that is only half the part of the journey, because I don't want to generate images that look like my data set, right? I have a data set, I add noise, remove the noise, create you similar looking images. Yes, that is interesting, that's creative. Okay, with all these images seen, you draw a new image that is totally out of your knowledge or context of these images, you can generate something creative. But that is where it stops. We want more fine control. I want to say that, oh, your two eyes are not aligned, you generated a new animal face, but suddenly the two eyes are not aligned. So then you start saying, no, this is not natural, this is not, cannot exist in nature. So how do I now bring the fine control? How do I allow, right, an external input into this process, right? We want to have control of this generation much more nuanced. So in this example that I am showing out here, how do I now introduce text conditioning, a robot painting a canvas, right? So this is what I want. So I am giving it as not generate any image, any data set like image. I am basically instructing it with very peculiar expressions. The simplest way you can think of is, if I have a random noise to image generator, let us say this is your full pipeline that we talked about in the diffusion backward process, if I have something like this, the simplest thought, in fact, what was came out as the first versions of text conditioned image generations had this philosophy. I just condition it. I just allow the text also to play a part, provide this, encode the text, give it as an embedding, the cross attention or some other formation in the denoising transformer should take this textual information into account and generate an image that makes textual sense. Right? An image could otherwise have made image sense, but it has to be also grounded on the text. So you start making the conditioning possible. But this set of methods had significant limitations. The fundamental limitation being the generated outputs rarely followed the instructions. For very specific peculiar tasks, the instruction following was possible. But the moment you start seeing things as complex as a robot painting a canvas, maybe it would generate a canvas, maybe it would generate a robot, but the interlinking between the objects mentioned in the text and its pictorial depiction, these are very hard. Right? These are very difficult, and the initial set of models like the architectures that I put out here did not go that far in terms of following complex expressions. So then came methods called latent diffusion models, or more generally what you call now as stable diffusion. Right? So latent diffusion models, particularly about, if I am not wrong, 2022 onwards, they have become the de facto for conditional generation. So what is it at a high level? Right? So a latent diffusion means we have some model which operates in the latent space of natural data. So let me just quickly introduce variational autoencoder. Of course, autoencoder is the simplest thing that some of you already may be aware of at this stage, which involves data that is encoded into a latent space and a decoder that reconstructs back the original data, and you perform a reconstruction loss to train the encoder and the decoder. In a variational setting, you are not trying to generate the direct latent space, but you are trying to predict the parameters of the distribution in the latent space. So suppose my latent space is has a random generator and it has certain parameters. Now the parameters, in this case the variational autoencoder uses a Gaussian noise. You only learn the mean and the variance, which are the only parameters needed to sample from a Gaussian distribution. So the encoder provides you the path to generate the mean and the variance, and now the decoder simply samples from this distribution, passes it through the decoder, and you get a reconstructed data where is a KL divergence loss on the encoder side, and there is a reconstruction loss also at the decoder, and the join loss is used. Not going into this is at least 10 years old, very popular approach in generative modeling, very popular in latent representation learning and so forth, right? So VAEs. So where is it used now? And if you put it into the diffusion setting, it is exactly put in the case you would think you would go into, which is that you do not try to perform the diffusion on the original image space. You try to perform it on the latent space. Okay. So let us first decouple the two boxes that I drew, meaning the top left and the bottom right. Assume that if you have some representation of the original image as Z, right? Now we talked about how to do text conditioning on any generation. So if there is a forward diffusion process that you apply on a data, use that forward diffusion to give you cues to train a denoising transform, and in this case we also want the textual embeddings and textual conditioning. So this whole box that is drawn with dashed lines is really the text conditioned diffusion model we talked about a couple of slides ago. Now what is the difference? The only addition is that you don't perform this on the original image space, you perform this on a latent space. You convert the image to a latent space Z, you do all your diffusion process, text conditioned diffusion process in that space, and then bring it back through a decoder into the original image space. Right? The whole rest of all the math and all the settings that we discussed in original diffusion perfectly stays. You are just introducing this into not at the original space but at a latent space. Right? Now, let us see an example, right? And then I will talk about a little bit more about why the latent space is a very good direction to pursue and why this has potentially seen a lot of success. So, let us take a complex text input, right? A text input that is potentially, let us say, otherwise if you directly condition on the image space, very difficult to make the model follow. You are asking several key things. You want a cute puppy, you want a type of the puppy called golden retriever, you want it to wear a red bandana, right? And then if you ask more, model will start abusing you, right? You have asked that much, right? And you want it to be sitting in a sunlit park and at sunset, right? The highest level of adjectives you can push the model to generate and follow, right? And you are going to be unhappy with anything that it misses, right? Typically we are, right? We have given so many different specific words, right? Even if it is orange, we start saying, oh, I asked you red, why are you giving me orange, right? So all this. So let's take this. What does it do? Now, this prompt is fed to the stable diffusion model, which we talked about. There is a denoising transformer or a UNet model, takes the text prompt, converts that text into some embeddings, right? Text is encoded, image is also encoded, and they interact. The encoding of the images is through the variational autoencoder style model, and the encoding of the text in a standard world is an LLM. Right? A large language model encodes your text, and this encoding coming from the text merged with a variational model coming from the image encoding is used to train your denoising transformer, and the denoising transformer purely predicts the noise that you have introduced in the latent space of the images conditioned on the text that you want. Right? You have to remove the noise but also line up with the conditioning given by the text. So what it does, it starts making the noise move into the step that you are after. Sunlit park, red bandana, a retriever dog, puppy, all that, right? And slowly this process evolves. Iteratively you are denoising it, iteratively you are generating newer samples. If you stop the diffusion process somewhere in the middle and start sampling what the image it came out, right? This is exactly what it is, right? You don't stop it though. You allow the diffusion to go through and then you decode through the variational decoder. But if you want to see whether the intermediate process is moving in the direction, this is probably what you will see, right? Intermediate steps also make sense, moving in the direction but has noise. And finally, you kind of try to get what you are after. The model follows this kind of behavior that you expected, then you start getting this response, right? By the way, all this illustrations were also through such a diffusion model, right? I basically asked the model, prompt the model to give me an illustration of how to do this, and then this text images and this prompt going in and the denoising transformer as well, all this comes out, right? So now let us compare them, right? So we talked about two models in the last half an hour or so, the general diffusion models and then the stable diffusion, primarily because of the text conditioning, primarily because, which also was new knowledge for me, this has not much to do with stability and so forth. This was coming from a company called stability.ai, which also caused the name stable diffusion. So what are these, right? These are general broad class image generation. But these are primarily text conditioned or input conditioned. Now there are also efforts to do voice conditioning, efforts to generate voice with text conditioning. generate video with text conditioning and so forth. So text to image is only one step of the way, and there are many other opportunities also that lie in here. Operates directly in the pixel, whereas these operate in the latent space. Now that is where you can see a lot of value. Remember that the pixel space is typically very high dimensional, right? You have an image, say a reasonable resolution 256 cross 256, which also would already start seeing a small resolution, but that still leaves you with 16K pixels. That still leaves you with the 64K pixels that you need to deal with, right? So whereas in the latent space you have a few hundred dimensions. So the denoising, the diffusion training and inference is significantly effective and faster. And conditioning is significantly effective and faster because now you are operating in a much lower dimensional space where you can control small degrees of freedom to align it with the text. If you had a pixel space to align it, it is more computation and memory heavy, and it is also more messy, right? So that is why latent space is much more efficient and perhaps the one that is the de facto for image generation. And finally, you can think of various applications. General diffusion is also possible if you want to run that for image audio generation, but a stable diffusion has a lot more to offer in terms of additional control. So where is it used, right? In addition to preparing the slides, right? It is used in several spaces. You can think of all possible places where you want to do as creative as a game set generation, graphic design illustration, storyboard visualization, creative art, right? In fashion and textile design, how would I look if I am wearing this Amazon or Agio dress, right? I want to paste my picture with this costume and then immediately visualize, right? Fashion and textile design. Interior design, you have a plan. You want to visualize how it looks in 3D. You want to visualize your home, your office space, your area before you actually generate this. In media and entertainment, right, significant use. Many of your VFX, your film production, your all these AI generated animations that you keep coming across in all the media and entertainment, significant use cases, right? Now it's almost ubiquitous, right? Gone are the days you purely shoot with a camera and release the movies and images out of those. You have to post process, you have to apply modeling techniques on top of it. Last but not least, e-commerce, right? Ad generation, synthetic data, photography of 3D version. So you might have product to sell, but you just put out only one photo of it. Now you're going to make a 3D version of it. You want to make a video of this, how to generate all this, right? This is again, even I would say, a very small subset of the whole applications. If you take medical world, if you take biomedical imaging and so forth, significant data generation, augmentation aspects related to stable diffusion are being explored. Thank all of you for your attention.